Ngalakin Khadijan Nyunga Boja.
Okay, let's go underground. So two broad topics within the extraction section of this unit. Surface mining, underground mining. My definition is simply, if you look upwards, you can see the sky, that's surface mining. Underground mining is a lot harder to explain than surface mining because you can't just fly a drone over and take photos, or you can't just stand on the side of the mine and sit. There's lots of rocks in the way. It's much more three-dimensional because you can go upwards, downwards, sideways. Whereas surface mining, basically, you can only really go down or sideways. And also, it's maybe older, got more old terminology. But luckily, recently, things like videos, cartoons, 3D animation have made explaining it a lot easier. So within underground mining, we're going to be looking at development, which I'll explain in a moment what that means. Then the mining methods, which are called stoping methods, and then how you choose between those various stoping methods. And there are about, I don't know, 5, 6, 7 common stoping methods. Equipment typically used, the ground control, how we stop rocks falling on our head, and ventilation, not something we have to worry about the surface mining, getting fresh air down there for the workers. So this is the first choice in any mining project, first decision. Do we go surface mine, underground mine, or some sort of combination? We make that decision based on the depth of the ore body. It is the most obvious one, I suppose. If it's 1,000 meters deep, it's probably going to be an underground. If it's 100 meters deep, it's probably going to be a surface mine. The shape and dimensions of the ore body. So if you've got an ore body which is fairly flat and tabular, then surface mining has advantages. If it's a more vertical vein type thing, then underground mining is maybe better because it requires you to remove less waste. In the depth of the ore body, of course, is not just the depth to the top of the ore body, but the depth to the bottom of the ore body. What is the ultimate bottom of the ore body? Geotechnical factors, by which I mean the strength of the rock, which is not just the physical strength of the rock in its tacked form, but also the number of fractures and cracks which it's had over its lifetime. The value of the commodity, I mentioned way up front, one of the driving forces is the low value of, say, iron ore, coal, low value per tonne, so you cannot afford to mine it expensively. And underground mining is inherently more expensive per tonne than surface mining. The grade and grade distribution, so that's the quality of the ore. Again, this really ties in with the value. If it's really high grade, you can afford to mine it expensively. If the grade has pockets of high grade which you just want to mine, then maybe underground mining is better because you can go and get little bits, whereas surface mining, to extract a piece of ore, you've got to extract everything above it. You don't have to do that with underground mining. Costs, obviously, always important, and as a general rule, surface mining is cheaper, both with capital and operating costs. Local labour skills, surface mining is easier, so some students drive trucks after 1 or 2 days training, whereas some of the underground equipment is fairly specialised and needs much more training. The project lead time, so that's the time between starting and your first production. Remembering you don't get paid until you've produced your first tonne of product, first bar of nickel, whatever it is, and sold it. And that typically is several years. So keeping that short is the ideal. And the good example of this is maybe Olympic Dam. I'll just switch to my whiteboard to explain that one. So Olympic Dam is probably the last major world-class deposit found in Australia. It has a mine life of
100 years, which is pretty amazing when you do the mine design and planning and try and work out what's the copper price going to be in 100 years' time. So it's copper deposits, gold, silver, uranium. So that's Olympic Dam down there. And it's under about 300 meters of waste material. Now, if you give that challenge to a mining engineer and say design the best mine to exploit the deposit as efficiently and successfully as you can, the answer is a large open pit. But as you can see, you've got to remove a lot of waste before you get to the ore. So removing this waste would take maybe, and these are ballpark figures, 6 years and cost $6 billion. But that's the best thing to do overall over the whole mine life. However, the company owned this, company called WMC, Western Mining Corporation. They couldn't afford $6 billion because you've got to spend 6 years and borrow $6 billion before you start getting any money back. They couldn't borrow $6 billion. They were only worth about $7 billion themselves. So what did they do? They could have obviously sold the deposit, but what they did was they went underground. So they said, okay, let's put a shaft down there. And then started mining underground, which is what they're still doing currently. Now, this probably cost them $1 billion and spent 1 year, but enabled a smaller company to start to exploit that. So they had to, due to the commercial realities of life, they could not spend that much money. They had to go with what technically is the wrong decision. Now, the interesting thing, of course, is WMC was bought out by BHP 10, 15 years ago for about $7 billion, the whole company. Now, BHP can afford $6 billion. That's petty cash out of the iron ore division, just a couple of months' earnings. And they did do a total redesign of the deposit and did propose to go with the open pit. And there was some wonderful, I don't think they're still online, the full feasibility was online, some wonderful statistics. They were going to pump water from the ocean about 500 kilometres away for the processing plant. They were going to take 40% of South Australia's electrical requirement for the processing. They were going to take trucks from Caterpillar, 6 months supply of Caterpillar trucks, etc., etc. It hasn't actually gone ahead yet for probably political reasons, but so they're still doing what is the non-best option technically.
Environmental issues. Surface mining, you are creating a larger hole in the ground. So if I said there's a gold deposit 500 meters below you now, assuming you're in a city, you probably wouldn't be able to do a surface mine just because the environmental cost of moving the city is too great. Whereas an underground mine you might be able to do because the surface expression can be quite small. Safety, surface mining is inherently has a slightly better safety record because you've got bigger equipment, more mechanisation, so less people per tonne, if you like, and less people, and also no rocks above your head to fall on you. So broadly, surface mining advantages: lower cost, which is always popular, safer and high quality working environment, which is people often prefer, the workers, a less skilled workforce, it's easy to get. Disadvantages really are this surface disturbance, and if you don't do it right, the area is large and visible and expensive. So, surface versus underground mining, safety. Normally, I take students underground in the underground mining 1 unit, the MPE, and a lot of them are slightly nervous about going underground, and safety is concerned. Almost all of them come out saying, wow, that's great. And it's not about running away and avoiding going underground altogether. It's about proper procedures, practices, training, and being prepared and reducing the risks. And I talked in the first week about the safety record of mining. It's not as bad as the public perception. All right, so with underground mining, we have these, we're often reduced to showing these schematic diagrams to show what's happening in a very 3D environment and to describe some of the terminology. So we've got an ore body here in this darker blue colour. We've mined it with an open pit. It's got 2 deep for the open pit, and then we mine it in this area. This is the mining area, which we'll come back to in a second. And then to get to that area, we need to have tunnels to get people down there, equipment down there, people out, and the ore out. One way is to drill a vertical tunnel, similar to a lift well in an office building, same sort of size, and people go up and down it, not in a lift, it's called a cage. And then you drill tunnels horizontally across to the ore body and you do your mining. So that's how people get down. Equipment gets down, equipment might have to be taken apart and then reassembled down there to fit in the shaft. And we mine. Then to extract the ore, to get the ore to the surface, we put it on front-end loader type things or trucks, take it over to here, drop it in a tunnel down to the bottom where there's a bin, little conveyor belt, a crusher, and then it's hauled up in a big bucket called a skip. Hauled up to surface, unloaded to the processing plant. The other method of getting access is with a decline. So from the lowest point, to reduce costs, we create a tunnel from the bottom of the open pit. Well, not quite the bottom, because that will be underwater often. So just above the bottom, you create a tunnel which is inclined and it spirals down. And then from that, you have again the horizontal tunnels across to the ore body. And then to get the ore out, you put it on trucks, similar to a surface mine, and drive the trucks up this decline, ramp, incline, lots of different words for it. So those are the 2 main methods. The difference, so this second one with decline is similar to open pit, truck and shovel, except the trucks are a lot smaller. The biggest truck which can fit in the underground tunnel is 65 tons, whereas the biggest truck in the surface mine is 365, so nearly 6 times bigger. And that's true of underground mining. It's just smaller scale, just because you haven't got the space. The decline is steeper, because the equipment's designed to go steeper. So an open pit, 1 in 10, a decline, 1 in 8, 1 in 7 is more typical. Notice down here, where the ore body probably extends, we've created a tunnel to give access to the geologists so they can do exploration drilling from there. And it's obviously a lot easier for them to do it from there and cheaper than to do it from surface. So hopefully they will define this ore body for the next year's production, and then next year the mining will occur down here and the exploration again will go deeper. So the stope is the zone in which the ore is mined. It's just a production area, volume. It's not constant in shape, even within a given mine. It's not the same shape every time. It will tend to be, but it varies because, of course, the ore body is not a perfect planar thing. It's going to curve and so on. Don't worry too much if you don't understand what stoping is now. We'll come back to talking about the stoping methods. It's just that area, the zone in which we extract the ore. Everything else, all of these tunnels here, which are required to get to the ore, are called development. So whether it's a vertical shaft, decline, even these, I didn't mention a vertical shaft there, which is just an empty shaft to get air in and out. All of those are just things we have to have. They are drilled, you'll see, in waste rock, so they just cost us money, produce no revenue. So we want to minimise those, but they are essential to get people, equipment to the ore and people and equipment back out again, and the ore out. So there's two broad types of underground mining. I suppose you get the development, which is fairly common techniques for all stoping methods, and then the stoping methods which differentiate and differ from ore body to ore body. Some definitions: if you imagine you're standing in section view in the ore, this is the ore, and either side of it is waste, so not valuable. Hanging wall is the boundary between the ore and waste above your head, and the footwall is below your feet. Fairly clear names. So they refer strictly to the boundary, but people also use them to describe this rock. So they'll say the footwall rock, meaning this waste here, or I came in from the footwall side, meaning the tunnel came in here. In any given mine, this will equate to west, east, north, south, or whatever, but people still will describe it as the footwall side, hanging wall side. One other term you need to know is the back, which is the ceiling, the rock above you in a tunnel. So let's look at the first one of those, development. So these are the tunnels. I'm not going to really talk about vertical shafts in this section, but all near horizontal tunnels, including the decline at 9.7 at the most. So they are providing underground access to the deposit to get equipment down there, get people down there and up, and get the ore up. Usually achieved, as I said, either with a decline or with a shaft, or sometimes in bigger mines with both. And this is a animation, or it's not an animation, it's a 3D schematic of a underground gold mine, and it shows just perhaps some of the complexity. So that's looking in section view. The green is an open pit which has been mined, and then we're mining it down there. The yellow is the stoping areas, the ore body. And then you'll see all the development tunnels in bluish cyan, whatever that colour is, and white and red. The red ones are ventilation. So this is just a 2-3 metre diameter empty hole to get air in or out, with a fan at the top probably. And all the others are just to get down to the stopes. So the stopes are the ones in this slightly yellow shady colour, sandy coloured. So you see there's a decline coming off the open pit up there somewhere, and if you follow it closely, you can drive all the way down to the bottom. It's about 1,000 metres to the bottom down there, so it'll take you quite a long time to drive down there. But that's the way you get access, and then there's various tunnels coming off that decline horizontally to get to the stopes and to take the ore out. But you see it's pretty complex, a lot fiddlier than an open pit, which is just really a two-dimensional surface. This is much more 3D, and you can attack the stopes from below, above, sideways, hanging wall, footwall, etc. So just to reiterate, how do we get people, equipment down and ore up? Either a vertical shaft, and then we come over to the ore body, in this case on the footwall side, or an inclined ramp. And then we come in this case, on the hanging wall side. Pretty hard to get photos of these. Here's a decline, and just driving down the decline. So these are typically 5 by 5 meters, are 6 by 6. And you just drive down in a Land Cruiser, nothing too high tech. This is sped up, by the way. This is over speed limit. And here's one, this is deeper, and it's got some lighting. You see this one's quite wide. Here's a truck carrying ore out of a decline. And yeah, that's it. You drive down the decline. As I said, if it's driving down 1,000 meters, it'll take you 30 minutes or so to get down there. Shaft, similarly, fairly difficult to get a photograph of. This is a ventilation shaft, so this is just for air, so it's got nothing, those equipment inside it, and it goes several hundred meters. This is one where you have got skips and cages, take people up and down, equipment up and down, and the ore out in the skips. This is during construction, looking upwards. It's a circular, reinforced with concrete, because this is going to be there for many years, so you want it to be stable. And then you put in all the what's called the shaft furniture, which is the pipes for water, air, computer networks, etc. It's hard to get a photo of the shaft once it's operating, because it's like going into a lift in an office building. There's things going up and down. You'd have to stop all production to get a photo. At the top is just what's called the head frame, which is just a winder engine at the top, which hauls things up and down on steel cables. Similar to, again, a lift in an office building. On the roof, usually, there's a winder which just hauls the lifts up and down. Now let's look at so these are the two ways of accessing. Let's look at how we do development in a horizontal or near horizontal, so including declines, mining cycle. Obviously, being a cycle, it's hard to say where the starting point is, but the most logical one is here, where you're drilling holes. So this is a section view on a rectangular shape, maybe 5 by 5. You drill blast holes using this machine called a jumbo, which we'll come back to. The blast holes are not very long, 4 or 5 meters. You then charge them with explosives. You then have to leave the mine and blast, and then you can't just walk straight back in and start mining, because there are noxious fumes from the explosives, nitrogen oxide, which we don't really have to worry about with surface mining, because the wind blows it away, dilutes it very quickly. Here we have to dilute it ourselves, so we have to have the ventilation system, and then you allow typically 30 minutes to dilute that dangerous air, the dangerous gas. Then we can come in and remove the broken rock, usually with a remote controlled loader. Here they're putting it on a truck, taking it away. Then the key point is you've advanced the tunnel 4 or 5 meters, but you haven't made this bit of the new bit safe. So you have to, this is a scaler, just knocking loose rocks off, and then you would put in rock bolts or shotcrete or some sort of system to make this new bit of the tunnel safe. And again, we'll come back to the systems you have. It depends on the geology and the strength of the rock. And then we're just surveying to find out exactly how far we advanced. And then you come back in and repeat this whole cycle. So drilling the holes, charging or loading, blasting or firing the holes, wait for the noxious fumes to be replaced, diluted, muck or bog the broken rock. One of these is Western Australian, one is Queensland. I can't remember which is which, to be honest. Make the new advanced part of the tunnel safe by installing appropriate ground support, so nobody's allowed into that new area until it's been made safe. Maybe survey it, find exactly what you've achieved, and repeat. So this first video here comes from Atlas Copco. No, sorry, this is one from Argyle, the first one, Argyle Diamond Mines, which is just about closing now. So this video is a few years old, but it shows just these steps. It doesn't have the survey step. Better than I have been able to explain it, no doubt. So we're coming in, this is a decline. Going across to the ore body, which is underneath the open pit somewhere. So we come in with our jumbo. We've got pipes there for fresh air. Here's our jumbo drilling 2 or sometimes 3 holes at once. So this is semi-automatic. There's no operator holding these drills. The operator's sitting in this cab here, which is safer and a lot more productive, obviously, to have 2 drills going at once. They wouldn't drill this fast in reality. This is obviously sped up. And then this is loading them with explosives, which is still a fairly labour-intensive process. Once that's finished, we'll leave and blast, wait for the fumes to go away, and then come in with a loader. So I said this would probably be a remote loader because it's safer. So the operator's not on the machine, they're either sitting or standing a fair way away. In this case, we're getting the rock out of the decline by putting it in a truck. And the next step is to make that new bit of the tunnel safe. And here again, with some instantaneous, lots of rock bolts. Again, you'll see it's a machine doing it. So the operator's sitting in the cab. The precise shape and spacing of these bolts will vary from rock type to rock type. Now, in this example, we're also spraying concrete. This is called shotcrete. Doesn't happen in every mine. And that's basically it. We're now ready to go and bring the jumbo back in and drill the next round. This video comes from one of the suppliers at the Copco, and it uses slightly different terminology because it's really not aimed just at mining, it's aimed at tunnelling in general. Also, I failed to mention, manufacturers feel the need always to put music on their videos. It gets a bit annoying after a while. If we look at the first step process in that cycle, blasting, or drilling, really, drilling and blasting are grouped together, looking head on at the end of the tunnel. So we're talking about dimensions 5 by 5, 6 by 6. And we'll generally have an arch shape because structurally it's safer. Anybody who's familiar with bridge design and so on, the arch has an inherent strength built into it rather than rectangle. And the challenge for underground blasting is there's nowhere for the rock to expand into. So with surface mining, you've got air above it, you've got air to the side, so it can swell. Here we've got rock on most sides of it. The only side is in and out of it, or in towards us, but most of it's surrounded by hard rock. So there's nowhere for it to expand into. You've got to persuade it to come towards us and also give it some initial air in which to break, which are what are called cut holes. So here, somewhere in the middle, you create these holes which are empty. And all they do is provide a little bit of space for these holes to then expand the rock. And then you try and persuade it with slightly inclined holes to blast towards us. Also, this is going to be the tunnel we're going to be working down, walking, driving down. So we want a nice clean shape of a specific size. Again, with surface mining, don't really worry too much about what the end result looks like. So we need a specific smooth wall, contour holes, lifters to make sure the floor's adequate, and so on. And you sometimes draw holes on the edge, again, to create like a piece of paper. When you perforate a piece of paper, so you rip off the bottom, it rips at the precise line you want. Same sort of logic. You create empty holes around the edge, or lightly charged holes to create the shape exactly as you want. But this is just a lot more complex than surface mining, because you haven't got the initial air to expand into, and you've got a precise shape you want to create. So there's an example. You see the holes on the edge to get the shape you want, and then these are what I call the cut holes in the middle, which are empty. So these are large-ish holes, just to put explosives in these and allow them to break into those. So the principle is to create an opening and then blast towards that. So this whole area is about 1 to 2 meters. That's called the box cut or burn cut. Seen this photo before. The powder factor, so this is the amount of explosives used per ton of rock, is much higher than surface mining because it's just more small scale. And you can't just put a lot of explosives and explode it. It hasn't got the space. And there you'll see in the back of the roof, the half barrels, as they're called. So it's broken exactly to where those holes are. So you've got precise shape you want, which is great. Here's what I might call a good drill and blast. So you see again, it's broken exactly to the outer holes where you want the shape. Looks pretty smooth. It looks inherently no boulders about to fall on your head. There's no ground support. I can see rock bolts, but it looks inherently strong. This one doesn't look so reassuring. You can see how the shape, the size has changed at each drill advance. So there's one advance, and then they've drilled again. It's changed section, and it looks like quite a few boulders. I wouldn't be too comfortable walking down there. I'd be keeping an eye on the roof, particularly as there's no ground support, no mesh, no shotcrete. So although it's probably safe, one of the disadvantages of this rough is when you pump air down it, it costs you a lot more to pump air down a rough tunnel than a perfectly smooth one. So it does cost you money, as well as not looking quite so flash. I'm just going to show now a video from ACG. ACG is the Australian Centre for Geomechanics. They are a research and training organisation. They're actually located in UWA. The video focuses really isn't really aimed at workers who are going to be actually working underground, talking about explosives and explosives handling. But it's only a couple of minutes long, I think worth watching.
The first step of the process is to drill holes to place the explosives inside the rock we want to break. Inside each hole, a primer is used to initiate the explosives. Several types of explosive products can be used to charge the holes. Essentially, the holes are filled with either packaged or bulk explosives. Primers are made of packaged emulsions or a product called boosters, combined with a detonator placed in them. The explosion exerts very high pressures way above the rock strength. This creates a zone of crushed rock immediately around the hole. The explosion also generates a shock wave which starts the cracking process. The explosive gases generated expand extremely quickly, forcing cracks apart, breaking the rock and pushing it into the nearest void. Long holes may use multiple primers. They are typically placed at the toe of the blast hole and then at predefined intervals as determined by the drill and blast engineer.
Speed it down about 10 meters.
Enough primers are used to ensure that the long explosive column is initiated.
Even though explosives are hazardous, if stored, handled, transported and used correctly, they are safe.
Explosives must always be stored in authorised areas. The different classes of explosives should be separated by physical barriers. For example, the detonator must not be stored with the boosters, packaged or bulk explosives. It is a good practice to display the storage rules inside the magazines, and only authorised personnel will have access to the explosives. Similar rules apply to the movement of explosives. They can only be transported in approved vehicles driven by competent and authorised persons.
Blasting is part of everyday life in a mine, and each site has specific procedures for firing. You should be aware of these procedures. A safety requirement to all sites is that everyone needs to stay clear of the area affected by the firing.
There will be barricades and signage to inform you. Employees must be in a designated safe area during the firing.
Well, the tag board is for safety. It lets us know who's actually in the working parts of the mine. So if there's anybody left in the mine, we don't fire.
3, 2, 1.
In most cases, access to the firing site is restricted until a competent authorised person has cleared the area as safe. There are three main hazards to be aware of after a firing: the fumes, the possibility of misfires, and changes to ground conditions that could make the area unstable.
So let's look at this cycle which we've been describing, and using an example of Cadia East, which is a large copper gold deposit in New South Wales, at the actual times and so on. How long does this cycle take, for instance? So they had a cycle with drilling the face, took them 2.5 hours. And you notice they're going 3.5 meters deep. Charge, which means load of explosives and blast. Fumes clearance, 30 minutes till they're allowed to go back in. This is where they sprayed water on the face to inspect it. So that took half an hour, safety. And then remove the broken ore. Then do hydroscaling and shotcrete. You've seen scaling in some of the videos before from Atlas Copco, where you just have a hammer which bashes the rock and loosens, removes any loose rock. This hydro implies it's got high pressure water, a different method. And shotcrete is the concrete sprayed onto the rock. Then put in some rock bolts. Then do a bit of a clean-up, remove any leftover bits which have fallen down from the hydroscaling and so on. And that's it. So it all adds up to just under 12 hours. So that will advance 3.5 meters every 12 hours. So you can see it's a fairly slow process. Obviously, these will vary from site to site, how many holes you have, how much ground support you need, etc. So in Cadia East example, you see most of the time is spent, well not most, but the largest proportion is spent on ground support. That will vary. If you're in really good rock conditions, that might be down to 10%. And the mucking and bogging is significant, and the drilling is significant. So each cut, or round as they're called, takes about 12 hours, advances 3.5 meters. So that's rounding to 7.2 meters per day. Unfortunately, we tend not to report progress in meters per day. We report per month, which is always silly because months have different lengths. So that adds up to be approximately 219 meters per month. Not sure where that opening bracket is, but I'm sure you can work it out. So that's a typical sort of advance. In fact, that's a pretty good advance. That hasn't allowed for any breakdowns, any operational issues, availability, etc. If we look at a decline going down, say 500 meters, the 1 in 7 gradient, that's 3.5 kilometers. It will take about 20 months to complete at a more typical 180 meters per month. So that's quite a long time. That's what, not nearly 2 years. So this is not a particularly quick process, and you need to plan well in advance. You can't just say, oh, let's put the decline there, we'll be there in a couple of days. It can take years. In terms of dollars, it's also very expensive, typically sort of $4,000 a meter. So that decline might cost $14 million. It's expensive because it's such small scale, only advancing 3.5 meters each time, fairly labor intensive, slow. So that's just the nature of development. I did a survey once of the tasks. Sorry, this isn't mine, this is theirs, mine's later. This is looking, they were trying to obviously improve the speed of the cycle. So if you change it from 12 hours to 11 hours, that's a major advance, major dollars saved and time saved. And they looked at the distribution of these tasks to see which one the most variable. And of course, it's not average bogging time, will not always be 90 minutes, etc., etc. And you can maybe look at the ones which vary the most and see if you can reduce that variation. Things they considered to reduce the cycle time, drilling faster, using different drills. Drilling longer, why only 3.5 meters? They tried 5 meters. Blasting more accurately, which should lead to less overbreak. Overbreak is where you blast and fragment it past the design shape, and less scaling, so loose boulders. Using electronic detonators, which are the most advanced in terms of timing, most precise. Trying to find an explosive with less gas emissions so they can get in earlier. Looking at the ground support, which of course is their main time. Looking at automation of the fibercrete or shotcrete, and improving the mixture so it sets earlier, because you've got to wait for that to set. And they tried all of those, and you can see this is their meters per day with time and gradually improving. The biggest change was when they went to from 3.5 meters to 5.5 meter blast holes, which obviously takes longer to drill, but you're advancing significantly more in one go. And this is the survey I did of development rates around the world, and I found there was a variation, and a mean around 180 or so was the sort of typical one, a few way up here. And if everything goes well in a given month, nothing breaks down, you have perfect systems, and a month with 31 days, people will claim a world record and so on, but they're pretty, they're abnormal, they're outliers. As an example, El Teniente, which is the large copper mine, the largest underground mine in the world in production rate in Chile. They plan to develop 98 kilometres of tunnels over an 8-year period. So you probably can't do that in just one development heading. You need to have several headings, several teams, several sets of equipment. So if you take 98 kilometres, divide by a number of years, which is 7, shall we say, number of months. So we need 1,167 metres per month. So that's probably 6 headings times 200 metres a heading is close to it. You might go with 7 to be totally confident. So you need a lot of equipment. Cost, the average cost is $4,000 per metre. That's a lot of money, $390 million. So you'd be looking at trying to reduce that cost, trying to improve the meterage, trying to reduce the kilometres if you can. All right, now the next section is looking at the actual stoping methods.